So I start saying good evening to everybody. The organizer of this call are me, Cosmo Pieri from Europa Uomo, Italy, the Italian Patient Association, and Tania Estapé, which is from the Spanish Patient Association, which in reality is a foundation, but the same type of activity. Today, the objective is to introduce this, let's say, to introduce the argument of biomarkers, because we see a lot of times in our activity, speaking about early diagnosis, speaking about multidisciplinary, speaking about with doctors, the term of biomarkers. I met in Budapest in the Congress Gianluca Ingrosso, which is a professor here in Perugia in Italy, and he has been so kind to prepare a presentation. The idea is the argument is not easy for at least for the people who don't have a scientific medical background. So I thought that I asked to Gianluca to give a basic presentation for what is possible, and in order that if this could be further say clarified, we can do other activities. We see speaking about liquid biopsies, we see with blood and with urine, we see people speaking about genetics, genomics, this and that, several type of genetic tests, and obviously for us is something not very known, not very clear. This is a seminar, is a webinar in the area we call of active surveillance. So, because in Europa Uomo, we have seen from our surveys with the people, with patients, that the patients say to us that active surveillance is very important when it's possible to be applied to preserve the quality of life. But we have seen during, we see always that this argument of biomarkers is not only related to active surveillance, is related also to all the other phases of in short, what I was thinking to consider is there is a sort of biomarker thermometer. So instead is a way to see in each person which is his situation biomarker, and this helps in all phases. It helps in the decision, because you can see. You can see in the decision of doing, for instance, early diagnosis, because if you see from this thermometer that you have higher risk, you are one of the people, the person who have the need to do the early diagnosis. Is better you do an early diagnosis. It's useful also in the multidisciplinary approach, because if someone after the diagnosis is seen that has more genetic risk, the treatment must be different. Okay, so, but let's say, I don't want to say too many stupid things, because I don't want to go and try to imagine the benefit of this type of scientific approach. So let's say that I will give the word to Gianluca, and the idea is that he will go through the questions that I put him, so he will go during the presentation looking after the question that we gave him. And obviously at the end it could be possible to have some questions session. More or less the question that I have is probably I and Tania gave him some questions, and the more I think are the same that we all more or less we now see: genetics versus genomics, somatic versus germline, hereditary male-female cancer, earlier control benefit for patients which have already had some genetic test, an idea what can happen in the family tree, type of test, relation with active surveillance. We don't want we cannot give all the answers this evening. We just want this to be an introduction. My idea is to have another webinar later in June, where there will be someone speaking about liquid biopsy opportunities. But probably today it's important. I don't know, Tanya, if you want to say something.
No, we are very motivated to organize these webinars because we think active surveillance is the future to avoid hard consequences of prostatectomy and other treatments. Mm-hmm. And Cosimo and me are very motivated. Even we would like to have more and more audience, but we are happy to welcome your 27 participants. So we are happy to listen to this speech on biomarkers. Yeah, thank you.
The good point is that these are persons from all the 27 associations, so will be the presenter to all the other persons. Okay, so Gianluca, we're sorry for the long introduction, and give you the word.
Okay, thank you very much, Piero and Tania. I want to thank all Europa Uomo, and I'm trying to share my slides. I don't know if you already see.
Yes.
Okay.
It's possible for all the audience to be on mute because some voices are here. Okay.
È quello che volevi? No. Dico, lasciami.
Okay. Okay. So I want to thank all of you for the time I can use the time you are going to dedicate to my presentation. First, I want to say that what Cosimo talked about, the kind of biologic thermometer, which is what I used to say to my patients when I talk about PSA, because I used the same example and say that it is a kind of thermometer. So I think it is a very good image. So very good image of what is a biomarker. Because a biomarker is something we use to measure something. It's a molecule, is histological parameter, is an imaging parameter that we use to identify a specific biological process. Why? Because in biology, it might happen that what we see is not what actually is, as you can see in this picture. So biomarker help us to discriminate, and we need biomarkers for the diagnosis and the cure. So they are very, very important. They are crucial. And talking about biomarkers, we can say that the genome could be the best biomarker because it contains all the information, all the genetic information. So the genome is the total genetic information in our cells and is composed by genes. So when we talk about genomics, we refer to the whole genome. Whereas when we talk about genetics, we refer to a specific gene or a set of genes. And we talk about genomics because now we are able to read all our genetic information through some kind of test, okay? Now, we know that the genome is the entire genetic information, which is made of genes. But what are genes? Genes are, I'll try to explain. We can say that humans are made of cells, and cells contain chromosomes, which are made of DNA. And DNA is a kind of biological code, which is composed by letters that make up words. So we can think of genes as words that are instructions for ingredients of a recipe. So we can think that genes are instructions to do something. Okay, so I take the example of carbonara pasta, which is a kind of pasta we have in Italy. We have the ingredients, so the instructions for the ingredients are pasta, eggs, and bacon, pepper, and cheese. Now, what happens if we change some ingredient? If we use pecorino instead of parmigiano, what happens is that our pasta will taste quite the same. So we made a variant in our recipe that works. We have a good pasta, okay? But what happens if we don't have spaghetti? We have a pathogenic variant that the recipe doesn't work. So we have a mutation, okay? And we can think, we can translate in this example into biology. Our DNA gets variation during our life, but some variation could be crucial, could be key variation that increases, these variations increase the risk of having a disease, of having a cancer. When we talk about cancer, we have to consider that cancer comes from the interaction of our genome with what is outside our genome, so the environment, lifestyle, and diet. So we know that we have our genome, which will have variation during life. We have variations because what happens that our DNA works very well, but we are programmed to live for about 50 years. Okay, so what happens that when we get older, our variation starts to accumulate. The variation in the DNA are, I can say, are typos in the DNA. And these typos starts to accumulate during life. So the more we get older, the more the risk of cancer. On the other hand, we have the environment, lifestyle, and diet, and they can increase the risk of variation. So that's why it is important to reduce the caloric intake, to eat fruits and vegetables, and to have a good lifestyle, playing sports, stopping to smoke cigarettes, okay? Because there are things outside our body that can affect our genome. Okay, now let's go back to our genome. We received our genome from our parents, and we have germline DNA, which is composed by the DNA of our parents. This germline DNA goes to all our cells. Our germline DNA is activated, or it's stopped in some is activated in some others stopped. And from our germline DNA, we have the development of all our cells, so muscle cells, fat cells, and blood cells. Okay, so our our cells come from an fertilized egg. We have germline DNA in all our cells. Okay, and prostate cells have germline DNA. Why we could think about studying our germline DNA? Because we have the DNA that we received from our parents, okay, that has specific variants. The DNA from our parents is a specific DNA which is unique and is a unique DNA, and the combination of this unique DNA gives us our unique DNA, which comes from our parents. Okay, so when we test something germline, we test our DNA of our cells, which we inherited from our parents, and we can taste our germline DNA with blood or saliva. Okay, why it could be interesting to test our DNA? Because it seems that we could have some kind of DNA fingerprint which increases the predisposition of getting cancer. The predisposition is different from the occurrence of cancer. Okay, what does it mean? Predisposition means that, as I told you before, during life we have several DNA typos, and the typos in the DNA increase during time. So the older we get, the more typos in DNA we have. When we have a predisposition, we start getting malfunction of our biology before a man that doesn't have the predisposition. So if we know that we have predisposition to some disease, we could try to prevent the onset of this disease. Okay, and this is just to show you that there are some studies going on, and here the study very recently published in 2021 is about genomic tests. So it is a genome-wide association study. It means that this study took into account all our genome, and the authors found about 300 variants in the DNA, which seems to be correlated with a kind of more aggressive phenotype, a kind of more aggressive disease. It has been tested in patients in active surveillance, and patients who sorry, I'll try to let's see. Okay, patients that are in this part of the curve, okay, in the top decile of this genetic score, or this kind of DNA fingerprint, they have a higher risk of upgrading during active surveillance. These are this test has been analyzed in active surveillance patients, in low-risk patients, and as you can see, here is the light violet and the violet curve, and as you can see here, there is a difference, a significant difference in the conversion-free probability, which means that the active surveillance went to an active treatment, okay, based on this genetic risk score. So it might be it is an interest field of investigation. We already don't have, in the clinical practice, we don't have tests for this kind of discrimination, okay? Another germline genetic test, it is not a genomic, but it is a genetic test because it takes into account BRCA mutations, okay? This germline genetic test is used in clinical practice, and we use this test to evaluate the risk of an aggressive phenotype. It could be used when we have the diagnosis of prostate cancer, and we have to decide about active surveillance. If a patient has a low-risk disease and is BRCA2 mutated, we can offer to this patient active surveillance, okay? BRCA2 mutated doesn't mean that that patient won't go active surveillance. We can offer active surveillance, but maybe we have to intensify the active surveillance strategy. Now, going back to germline and cells, I said that our DNA comes from our parents. And as you can see, we have germline DNA in our prostate cells. What happens that during time, our DNA has typos. And what happens that some typos, some variation are pathogenic, they are mutation, and they cause cancer, prostate cancer. And when a cancer is developed, this disease has a specific DNA, which we can find only in prostate cancer cells. And we call these kind of mutations somatic mutations. We can find somatic mutations only in prostate cancer cell, only in the tumor cells, okay? And these kind of mutations are under study. We are studying this kind of mutation. Why? Because we want to know the cancer biology. Here I show you a project which is called the Cancer Genome Atlas. And this project is going to map several types of solid cancer. As you can see on the top right of the slide, here we have the summary of the solid cancer mapped, and we have also prostate cancer. We have the database of about 2,000 prostate cancer patients. And as you can see, all the genome, all the 20,000 genes have been mapped. And for prostate cancer patients, the Cancer Genome Atlas reports about 27,000 mutations. Okay, here there is this histogram showing the more frequent mutations. So this is research. We don't have data in clinical practice about the Cancer Genome Atlas. This is a study, this is investigation, okay? Whereas in the clinical practice, there are some commercially available genomic tests. And these are based on tissue samples, okay? It's very difficult to have studies on circulating cells, okay? When we have to study the genome of the prostate cancer, we have to study it in the tumor tissue, because we are more we can get more details, and all these tests come from the whole prostate tissue. Okay, that means that these tests have been evaluated and validated. These are all prostatectomy specimens. We have Decipher and Oncotype. I mean, I think that these are the most known. And Oncotype is also used in breast cancer, and they are used in the US, but they are used to understand when and how to intensify or de-intensify a treatment strategy. They are not currently applied in active surveillance, for instance. There are some data on active surveillance, but I want to say that there is no uniform consensus on the use of these biomarkers, of these tissue-based biomarkers. There are no head-to-head comparison. The validation of these genomic tissue-based biomarkers are mainly on retrospective studies, so low level of evidence. So there are several issues, and although used in the USA, the American Society of Clinical Oncology do not recommend the routine use of these biomarkers. Okay, so in clinical practice, they are not currently used. They are commercially available. We can think about their use, but there is no defined specific subset of patients. And I can say that these biomarkers need to be tested in active surveillance, because they have been developed to decide how to treat a patient who need an active treatment. And for instance, Decipher has been developed to decide how to treat a patient after prostatectomy. Okay, so going back to our cells, we said that we have germline DNA, and we said that cancer comes from the interaction from our germline DNA and what's outside our body. And another thing, very interesting thing, is epigenetic. Epigenetic is chemical reactions that are around our DNA, and we can say that epigenetic is the memory of our DNA. Our DNA is a memory. So if we, if I smoke cigarettes, my DNA gets memory of what I do during my life. Okay, so that's a very interesting field of research, because the genome is read one time instead of 10 times because of epigenetic. Epigenetic regulates our DNA. So it's very interesting. It's a new field of research, and there are some drugs that are used not in prostate cancer, but there are some drugs that are used based on the epigenetic variations. So why I'm stressing the concept? Going back to genome, I want to talk about this, because I said that we have a predisposition inherited from our parents, and we know that from epidemiological studies. As you can see, there is a correlation between the family history and the risk of getting prostate cancer, and also family history of breast cancer and prostate cancer. If we have parents or siblings with prostate or breast cancer, we can have a 60% increased risk of getting prostate cancer. Okay, this is a very nice chart where you can see that this is a study from the Sweden registry. If the general population has a 5% risk of getting prostate cancer at 65 years old, a man with father and brother affected by prostate cancer has a risk of 30% at 65 years old. So we have a very increased risk of having cancer. And so that's why our family history is very important. So if we have a family history of prostate, breast, ovary, and prostate cancer, we know that there is a kind of predisposition, which means that we won't have cancer, but we have an increased risk. We have a predisposition. Having our brother with prostate cancer doesn't mean that we will have prostate cancer. We have an increased risk compared with the general population. And we know that the BRCA genes mutation mutations increase the risk of getting cancer. So if we have a family history, we can think, we can talk, we can have a genetic counseling and talk about the opportunity to get a BRCA test. Okay. We don't have in clinical practice. We don't have this scheme. This picture shows that we have germline DNA and we have mutation in the
First of all, I think Gianluca has an internet problem.
Okay. It seems strange. Maybe I ask him to reconnect.
Yes, because it will take him 2 minutes to reconnect. So just make sure that he is going to be reconnected. Well, till Kosovo communicates with Gianluca, I take this opportunity to remind you that we are okay. Then Gianluca is back.
Yes,
Thank you.
sorry, I had some problem with my Wi-Fi. So I'm going to close my presentation. So I was trying to say that we don't have germline test for our cells. We know that we have the BRCA mutation test, which is a germline test, okay, and is the only one we use today in the clinical practice. We have several tumor biomarkers. So germline biomarkers for our cells are under investigation. We have several tumor biomarkers for prostate cancer. We have serum biomarkers, urine, and tissue-based biomarkers. But the best biomarkers we have today is PSA. Then we have PSA derivatives like the prostate health index, which is a PSA isoform, and is very useful because it seems to be correlated with an increased risk of upgrade during active surveillance. And we have the 4-kallikrein test. The PSA is a kallikrein, is a molecule which comes from the prostate, and there are several kallikreins, and we can test 4 isoform of kallikreins, and they can be useful in order to better discriminate between clinically significant prostate cancer and cancer that can be observed. We do not need to treat that cancer. So it discriminates between clinically significant and insignificant prostate cancer. Another interesting thing is to combine. We know that MRI has a crucial role in the diagnosis and also during active surveillance, because we are using MRI during active surveillance before the confirmatory biopsy and during follow-up in order to get a fusion biopsy if we need to analyze the what we call the index lesion. So there are many studies analyzing the combination of biomarkers and MRI. Okay. So I'm trying to conclude. I think I gave you many information. So I hope my presentation has been clear. I don't know, but starting from genetics versus genomics, genomics refers to the whole genome, and genetics refers to a specific gene. We have, talking about genetic tests, we have the BRCA genetic test, which can be used for patients undergoing active surveillance, or it can be used in order to better define a treatment strategy. We have tissue-based, genomic tissue-based biomarkers like Prolaris, Decipher, and Oncotype, but they need further investigation. Okay. Then, talking about somatic and germline, somatic refers to tumor DNA. So if we are looking for somatic mutations, we are looking for mutation within the DNA of prostate cancer tumor. Whereas if we are looking to germline mutation, we are looking to our germline DNA. So we can have a BRCA mutation, which can be somatic within the tumor, or can be germline. The patient can have a germline mutation of BRCA, okay? So it's different. The same mutation, but in different cells. We have germline mutations. When we search, when we want to find a BRCA mutation, we test the germline and the somatic, both, okay? Then what about hereditary male, female cancer, and an idea of what might happen in the family tree? We know that from the epidemiologic point of view, we know that there is a correlation between family history and the risk of cancer. But I think that solid cancer that comes in the adult age and after 50 years is a multifactorial comes from many interaction between genome and what's outside our body. So we can have a predisposition, which means that our risk of getting cancer starts before a man that doesn't have that predisposition. But I said that cancer comes because there are typos in the DNA. Every one of us will have typos in the DNA. A patient with a man with a predisposition is a man that will start before the age of 50, typos in his DNA. So when earlier control, when we have a family history or we have a mutation in BRCA, we did the test because we have a family history. So it could be useful to start before the age of 50. Now we know that if we have to screen a population, we have to start from 50 and stop at 69. This is what our European guidelines and also the US guidelines say. So when perform the PSA screening from 50 to 69, when start earlier, when we have a family history, for instance, of prostate cancer or of breast cancer and ovarian cancer. I mean, breast cancer is correlated with BRCA mutations. So we could think of asking or getting the test in these subjects, okay? What are the benefits for patients already diagnosed? If we know that a patient has a BRCA mutation, BRCA2 mutation, we can think about using PARP inhibitors during his treatment strategy. Or if this patient is under active surveillance, we need to intensify the protocol. We need to do more frequently PSA, for instance, or perform the MRI and follow with more follow-up visits this patient. We will think about the use of a genomic tissue-based test, but this is quite investigational. I mean, we have commercially available tests, genomic tissue-based tests, but to date, we have no data to use them routinely in a clinical practice. What about the spectrum of tests? I said we have blood, urine, and tissue-based biomarkers and tests. PSA, I think PSA is the best test we have today. There are PSA derivatives which maybe will come in the clinical practice. They are very interesting for the active surveillance patients because they, as Cosimo said, they are kind of thermometer. So we can use them to better discriminate. These are biomarkers that can add information in order to know if a patient in active surveillance is going to have a change in his phenotype, in the phenotype of his disease. So when insisting to get a test, I think there is no answer at the moment. What is useful is to have genetic counseling to better analyze the tree, the familiar tree, and to evaluate if it could be useful to have, for instance, the BRCA test. Okay, what are the relation to active surveillance? Well, as I said, I showed you a germline DNA fingerprint, which could be useful in the future. We can think that in the future we will be able to go towards what is called personalized medicine. This is the goal of medicine. There is no more one fits all. We are going to develop personalized treatments, personalized diagnostic exams. We are going to think about cure a single patient for a single disease because we are unique. Our disease is unique. The interaction between the host and the disease is unique. There is a very high interest in the tumor microenvironment because we know that this microenvironment has a crucial role in the control of the disease. We know that the tumor has several pathways of immune escape. And we know that the immune system has a crucial role in controlling the onset of a disease. So there are in the field of oncology, there are several interesting and investigational interesting field of research. I can say that regarding active surveillance, it is a very important treatment option. And I'm very happy that men are getting this kind of treatment because about 40% of diagnosed prostate cancer are not clinically significant. We know that Gleason 6 can be considered a very, very low-risk disease. Although a recent genomic study in patients affected by low risk, so grade group 1, Gleason 6. The genomic study from the University of San Francisco showed that in about 6% of active surveillance patients with low-risk disease, there is a genome. So there are DNA mutations, somatic mutations, which are shared with a more aggressive disease. So we need to use clinical data, so PSA, T-stage, with MRI, the Gleason score, the age, and so on, in order to stratify patients. But new tools are coming for better stratifying, and this better stratification will lead to a better treatment strategy, a more tailored treatment strategy for all the states of disease. I hope that my presentation was clear. I don't know if you have any questions. I'm happy to answer.
Thank you, Gianluca. Obviously, we had already the idea before, but now even more that this is a very high-grade equation, and it's really good to be part of this evolving moment, because we are really see something changing under our days, in the days and the weeks. Obviously, I think, in fact, that the importance of this research is so important for many areas, and so I think it was very good for us to have this first idea. I don't know if there are questions. Probably there are many questions, but it's already we could have some now, but then we could or think about an email conversation or do something different. We'll see. Anya, do you have some written questions?
No, there are not. No questions at the moment in the chat.
Okay. There is someone in the group here that wants to put some question.
I only want to say thank you, because it has been very clear, being a difficult topic. I think it has been very clear with also pictures, examples that have been done it very, very interesting. Thank you.
So we probably need to take care of these arguments and wait for the clinical application during the years, because it's something that is really evolving. Normally now, let's say in the technological world, the new devices are very fast to be used, because you can say the phone, the smartphone, everything is coming immediately in use. But it's easier because probably with the body, with all these number of genes and cells and things, the number of variables in place are incredibly high. So it's very, we need to wait and wait for some development in time. Do we have an idea, Gianluca, just a rough idea when this could be in clinical use? Let's say in a big number. It will take 5 years.
Yes, I just want to say that some biomarkers like the 4-callicrine has been used in Europe and more specifically in the UK, because data from 4-callicrines comes from the PROTECT trial. Patients in the PROTECT trial received this test, and they were mainly low risk, but there were patients with intermediate risk and also some high-risk patients. And for kallikrein was a positive for kallikrein test was associated with a clinically significant prostate cancer. So this is a very interesting result, because we can think that having the 4 kallikrein test will allow us to better discriminate those patients with low risk or grade group 2, so Gleason 7 3+4, which may have active surveillance or need to be treated with an acute treatment. So I think that PSA derivatives like for kallikrein and prostate health index will be available because they are easy to get, and whereas the genomic tests are more complicated, they have a higher cost, and they need to be validated in prospective trials. For kallikrein has been tested in the product, which is randomized open label prospective trial. So he has a strong methodology, whereas yes, data from genomic test comes from retrospective trial. So this is a methodologic retrospective trial have a weak methodology.
The 4K, because we saw in some, it seems the number used for television, but it's not that. It's another 4K. No? You say it's 4K. Kaling is the name of a person, I think.
Yes, it is 4 kallikrein test. Yes, kallikreins are molecules like PSA.
Ah, okay. Okay.
See, PSA is a kallikrein. It is a protein which is produced by prostate cells, and there is a certain level of kallikrein in the blood, because kallikreins goes out with the seminal liquid. And we have a certain concentration in the blood. So the differences in concentration in the blood of kallikreins are correlated with prostate architecture destruction, so with prostate cancer. And that's why they have been tested, they have been isolated and tested. There are other biomarkers, tissue biomarkers like P10 loss or Ki67, which is a proliferation index. For instance, the Ki67 is used in the diagnosis of breast cancer in histology of breast cancer, whereas in prostate cancer we have only morphologic data of the 2 patterns of disease, the 2 patterns of Gleason score. It might be that in the future we will have some they are called histochemical data on the tissue. It might be. I think that PSA derivatives will be the easiest to get in the future. Whereas for genomic tests we have to wait. I don't know how many years, because I can say 2 years and I get wrong, because there are new insights. I mean, if we think about NCCN guidelines for prostate cancer or for breast cancer, they are updated 2 or 3 times a year. So there are new information and new data practice changing within 6 months. So it's very fast. So that's
in any case, something of what you explained will be happening soon. Something more complex will need more time. Certainly.
yes.
Good. I think it was very good for me, the presentation. I hope also for the other attendees. I think we if there are no other questions, yes.
Cosimo,
We
Daniel
have a
has
question.
Daniel
Sorry.
Ask has raised his hand. So maybe he has a question.
No, I'm not a question, but I had a comment about how we do it in Norway. In Norway, there are 10% get the genetic prostate cancer. So the health authority have said that a patient with metastasis and a patient with aggressive, also Gleason score 8 or more, and the patient who are get his diagnosis before 60 years, they have to take a genetics test. So that's how we do it in Norway with the genetic plus the family reason.
But do you get the BRCA test?
PSA, PSE.
BRCA test.
Yeah.
Is that the genetic test you get?
I think there's a lot of them genetic tests. Yeah, the BRCA 1 and 2.
Okay. Here in Italy, we use, but is used, I think, in all Europe, in clinical practice for patients after the genetic counseling, or in patients with an aggressive disease, because we know that in those patients, during their story, they will have a treatment with a drug called PARP inhibitor. So it is important to know if those patients have somatic or germline mutation, because if they have somatic or germline BRCA2 mutation, we can use PARP inhibitors.
Okay, thank you. Do you have some other questions, Anya? Or?
No, that's okay.
No. Okay, so I think we can close. We may close and.
Cosimo,
Yes.
just before you are closing, I would like to make a comment. First of all, thank you very much, Gianluca, for the perfect presentation. We are very much appreciating your very interesting slides that you have shared. And I hope that we will get them also, each one of us, by email, this presentation. And I have seen the names of the participants, and I have seen also the list of the participants to our General Assembly, that it will take place in Larnaca at the end of May, and I see very common names. So on behalf of the board and on behalf of Europa Uomo Cyprus, I would like to extend our full hospitality and welcome whenever you will be arriving in Cyprus, and it will be a great pleasure for Europa Uomo Coalition and for Europa Uomo Cyprus to host you and to spend 3 lovely days together. Thank you, Cosimo.
Thank you, Johannes.
Thank you, Johannes.
We will come.
So we can close now, and thank you for everyone to attending.
Thank you very much.
Let's keep in touch because okay.
Thank you.
Bye.
Bye, everyone.
Bye. Thank you very much.
Thank you.